Okay, so guys, this is what we're going to do today. And maybe if you do want to glance at your book for a moment, that might not be wildly inappropriate. But guys, what we're going to do today is we're going to begin a conversation about chemical kinetics. How fast do reactions go? So you ready for the overview of the entire unit? It goes like this. The first thing we're going to talk about is how fast do reactions go and what can we do to change that? You already know the answers to these questions. You guys remember when you drowned the Alka-Seltzer in dilute hydrochloric acid last year, and you made that reaction go faster by probably adding more acid or grinding up the Alka-Seltzer or by heating it up? Guys, that's what you were doing, is you were fiddling around with chemical kinetics. What we're going to do now is we're obviously going to go into this deeper, and we're going to talk about these things mathematically. But guys, let me give, and this will skip right off of you right now, but I'm going to say this now. Guys, we do this for one reason and one reason only. This is how you're going to be held accountable for this on the AP test. You ready? This idea of how do we make reactions go faster is no longer the end unto itself. It's a means to an end. Do you understand what that means? So the idea is that last year, the rates of reactions was the end. Hey guys, guess what? You can change how fast reactions go, da-da-da-da-da. If you understand it, you're done. Guys, this year, it is going to be a means to a bigger end. And that bigger end is what we call reaction mechanisms. Because when we study how fast reactions go and what changes how fast they go, we can peek underneath the covers and we can figure out what is going on behind the scenes in a chemical reaction. So guys, if you know that carbon and oxygen makes carbon dioxide, because it does. Carbon and oxygen makes carbon dioxide. We know the reactants are carbon and oxygen, and we know carbon dioxide are the products. What we don't know is what happens when carbon and oxygen turns into carbon dioxide. How does that happen? And that's what we're going to talk about this unit, and those are what are called reaction mechanisms. So guys, the big idea then, whoa, those are a lot of notes. Guys, the big idea then becomes this. We are going to talk about reaction rates, but we're going to move that into reaction mechanisms. Then when we're done with that, as we get into the next chapter, we're then going to talk about this. Remember this? Equilibrium. Guys, what is going on at equilibrium? Forward and reverse processes are happening at the same. Get the connection? So guys, that's the way this unit's going to unfold. We're going to talk about rate and how to change it. Then we're going to talk about what we can learn about rate. That's reaction mechanisms. And then guys, we're going to talk briefly about when rates forward and backward are the same. That's equilibrium, and that'll be the unit. You get the idea? Okay, so guys, today all that we're doing is setting the stage. I would say don't write this down, but I'm not that stupid. So everybody get ready to write down every single word. You ready? You guys are going to write all this down. All right, so ready? Here we go. What are chemical kinetics? Guys, chemical kinetics is the study of speeds of reactions. Man, you guys really are going to write all of this down, aren't you? You abbreviate? Realizing that with this group, abbreviation almost feels dirty. Some of your classmates are going, how dare you abbreviate? You got to write down every letter or you're not taking notes. All right, guys, here we go. So when we talk about chemical kinetics, we're talking about reaction rates, which tells us how fast reactions go. Last year, you learned this, that there are factors that influence or determine how fast reactions go. You are now thinking about Alka-Seltzer tablets. So guys, in order to get the Alka-Seltzer to react more quickly with the acid that you dunked it in, one of the things you could have done is change the concentration of the acid. So guys, why does concentration change the rate of a reaction? The more concentrated something is, what's the key idea? That's it. Say it again. Collisions, right? In order for two things to react, they have to touch. We call them collisions. The more of something there is, the more frequently they will collide. So guys, remember when we talked, and maybe you're not remembering this, remember the two things about collision are frequency and magnitude? Remember that? So is concentration a frequency or a magnitude issue? Frequency issue. So the why there is frequency. Can I show you what my daughter made me for Christmas? It's a holder. She actually made this in her 7th grade woodshop class. We'll talk later. I want you to know I'm going to tell my daughter you said that. So guys, concentration. What's another thing that you did to that poor Alka-Seltzer tablet? Well, you heated it up. You actually heated the acid, but you heated it up. And guys, again, thinking about collisions, when you heat up a reaction, does it change the frequency with which they collide or the magnitude, the amount of energy with which they collide? Both. This is double dipping. It's both frequency and magnitude. Maybe you've heard these rules that say every change in temperature of 10 degrees Celsius doubles the rate of the reaction. That's all phooey. But temperature does, in fact, change the reaction rate. Then, guys, what was the other thing that you did to that poor Alka-Seltzer tablet to get it to react more quickly? You crushed it up. But we are not going to just say crush it up, which was a matter of surface area. Guys, it's actually, we're going to talk about its physical state. That can be a lump rather than a powder, surface area. But we're going to talk more generically about physical state. But guys, physical state, if you want to think of it in terms of surface area, is that a question of the frequency or the magnitude of the collisions? The frequency of the collisions. Good. So that Y is a frequency issue as well. But guys, understand, we're going to make this more generic and not just talk about surface area, because that gives us space later to talk about catalysts, which are really cool. But you're going to be really frustrated because, guys, I understand just about nothing when it comes to catalysts. And so we're going to talk about catalysts we're going to talk about everything I know, which is pretty much close to nothing. So guys, when we talk about catalysts, we are actually talking about spectator substances that encourage reactions to take place, but they aren't included as reactants or products, and we'll talk more about that later. But understand, guys, catalysts are substances that change the rate of reactions, but they're not a reactant and they're not a product. They're neither, or both. And we'll talk more about that. Guys, sometimes a catalyst is just a surface upon which the reaction takes place. Sometimes a catalyst goes in as a reactant and comes out as a product. So there it's technically both a reactant and a product, which still makes it a spectator because it goes in and then comes out unchanged. And you'll find out this is all about what we call homo and heterogeneous catalysts. And we'll talk more about that later. So guys, there's the background. This is everything you learned last year. Anything y'all need to talk about? Remembering that the big idea here are collisions, frequency, and magnitude. Y'all good? Okay. Can I tell you about the one happy thing I did learn over Christmas break? Longmire. Have any of you seen it? Don't watch. No, it's a series. It was originally an A&E series, and then Netflix bought it and released a couple more seasons. Don't watch it because the language is horrible, but if you do watch it, it's really good. It's like super addicting. But if you do watch it, I didn't tell you to watch it because that's not okay. But it is really good. It's called Longmire? No. Yes. No. No. But if it were called something, it would be called Longmire. Here we go. Okay, so guys, when we talk about reaction rates, again, I know that you need something to build on here. So guys, some of this we talked about last year, but reaction rates simply measure the speed of a reaction. Now we're going to talk more specifically about how we describe rates of reactions, and we're going to start collecting a little bit of data. It's going to be contrived, but it'll work. And we're going to start studying some really interesting things about reaction rates that are going to make sense, but they're almost so obvious you'll miss them. So guys, when we talk about speeds or rates of reactions, when we talk about speed, it's how fast something changes in a given interval of time. And guys, some of you right now read this sentence and you start sort of having this little twitch that you developed in your calculus classes. Because you start thinking about time intervals. And when you start thinking about intervals of time, you probably start thinking about derivatives. You start thinking about first derivatives, second derivatives. If you're doing the AP physics class right now, which is calculus based, you start thinking about position and velocity and acceleration. And all of those things are true. And you don't need to know any of that. But if you do understand the calculus of things like change, understand this all ties together. You just don't need to know the calculus of it for this class. This is all going to be algebraically based for us. So, guys, when we do this, we need to talk about units. So, guys, we're not going to spend a lot of time on this, but let's talk about some familiar fundamentals. So, guys, when we talk about speeds, what are things in your life that you measure the speed of? Your car. And you look down at your speedometer and it tells you your speed in what units? Miles per hour. Other things you measure the speed of? Days per day? Okay, so one, is that a rotation or a revolution? Revolution. So revolution. So one rotation every 365 days. Whatever it is, it doesn't matter. So all right, you guys are coming up with nothing. So you ready? For some of you, this could be the most important thing you learned all year. Okay, so guys, you're driving your car, and you've got one circle thingy that tells you how fast you're going in miles per hour. Then on the other side, there's this other mysterious circle thingy. And when you push on the little pedal, it does this. So guys, that's actually tracking how fast your engine is spinning in what units? RPMs, revolutions per minute. So guys, that is actually measuring how fast the crankshaft inside of your motor is moving. You step on the gas, vroom, and it goes. And so that's measuring revolutions per minute. My bike computer does the same thing. When I pedal, I've got another display. I've got this little inclinometer that attaches to one of the crank arms on my pedals. And when I'm pedaling, it actually tells me my cadence, how fast my pedals are spinning, again in revolutions per minute. So let's stop there. So guys, we've got revolutions per minute for bikes. We've got revolutions per minute for engines. We've got miles per hour. All of these things are speed. The question is this: what do they all have in common? They're all per unit time. So guys, whenever we measure a speed, it is always in relation to a unit of time. So, can we not write this down? Similarly, when we measure speeds of reactions, it's got to be in relation to time. Don't write that down. Should I delete it? I know. So guys, let's do this then. What would be reasonable units to use to measure the speed of a reaction? Well, we understand that if we're measuring the speed of our car, what cars do is they travel through distances, so we want to know the distance, miles per time, hour. But guys, chemical reactions don't move typically. So to measure the speed of a reaction in centimeters per second, that's stupid. They're not moving. So what do chemical reactions do that we could measure per time? They change amounts of stuff. What do we call the stuff that's going away? The reactants. What do we call the stuff that's being made? The products. And what units do we use to measure amounts of reactants and products? Moles. So guys, our units for rate are going to be moles per minute. For now. What you're going to find out is that minutes are way too long of a time period. Typically, we're going to, you know what, let's just do that right now. No, you'll see. I left it in moles per minute because I lifted an example out of the text and it's given in moles per minute. But realize, guys, really we're going to go per second because minutes can be way too long on the order of very few chemical reactions go over minutes, right? They're just one and done. They're pretty quick. So do you understand what we're doing for measuring rates of reactions? Okay, so guys, here's what we're going to do. Don't write this down, but we are going to study a reaction. This is all hypothetical. And guys, let me just tell you right now, it is really hard, forgive me, at the dumbed down level of AP chemistry. And I know some of you appreciate this. Guys, I know AP chemistry seems like, holy stinking my goodness, this is crazy. But guys, in the bigger chemistry world, this is still like training wheel chemistry. Okay? In this world, it's actually really hard to find examples of reactions that are simple enough that they're going to line up with what we understand about kinetics. So even on the AP test, you're going to see that instead of giving you real world chemical reactions, they're going to give you hypotheticals like element A turning into element B. It's not boron and there is no element A. These are hypotheticals. And guys, you're going to see many times we have to deal in hypotheticals because we've got to come up with systems that work given our understandings. So we're going to talk about whatever A is, which we're going to represent with red spheres, turning into whatever B is, that'll be blue spheres. And guys, we've got this. I just lifted this. Is this still in our textbook? It was in the previous one, the old edition. Oh my gosh. I'm actually glad I'm using mine. Because if you look at page 559, they now have them in Florence flasks that kind of look like it could be chemistry. In the previous edition of this book, they had it in mason jars. I like that better because you can clearly see this ain't chemistry. They kind of doctored it up in the new edition, but we're going to stick with mason jars. So guys, what we're going to do with this, and you don't need to look at the book, we're going to collect some data. And guys, this is the data that we're going to collect. The amount of time that's gone by and the amount of A and the amount of B that are in the mason jars. So guys, let's look at time 0. Let's collect some data. Guys, A is the red stuff. So how much red stuff is there at time 0 when the reaction hasn't taken place? Because as the reaction goes on, what does the red stuff turn into? Blue stuff. So when the reaction starts, we're going to say that it's all red stuff and no blue stuff, and we're going to say that the amount of stuff is 1 mole. Get the idea? Okay, now, 20 minutes go by. Notice our high-tech timing device right up here above. So guys, here, see it? 20 minutes go by, and after 20 minutes, what happened to some of the red stuff? It turned into blue stuff. And guys, they actually give us some numbers. After 20 minutes, but how much blue stuff will there then be? 0.46, because the red turns right into blue. Get the idea? Guys, this is now interesting point number 1. 20 minutes later, in the first 20 minutes, we lost 0.46 moles of red. Where did it go? Blue. Turned into blue. So guys, 20 minutes later, will we lose another 0.46 moles of red? No, more or less? Less. Guys, it turns out that in the next 20-minute time span, we are only going to lose 0.24 moles of red. And again, where did it go? Turned into blue, so how much blue is left? 0.7 moles. Does this sound familiar? What does it sound like? half-lives. Guys, these are half-life processes. We're going to describe that mathematically later in the unit. But guys, the same logic that you applied last year and this year to half-lives is applying here as well. But now, guys, let's talk about why. Don't miss this. This is a huge, I know this is mason jars, but this is huge. So let's look at what's going on. So guys, in the first 20 minutes, we lose 0.46 moles of A. Let's call it red and blue. 0.46 moles of red, it turns into blue. In the next 20 minutes, we only lose 0.24 moles, about half. Half-life. Guys, we lose about half as much of the red turning into blue. Here's the question. Why? Given all the stuff that you wrote down on the very first page of your notes, which you didn't need to write down because you knew all that stuff anyway, guys, why? What explains the fact that the speed at which red is turning into blue is slowing down?
Reaction rate, like there's less amount, like, because of the things that influence, like, I don't know, since there's fewer.
Yes? Okay. Go ahead and finish this up. And so what's changing? Concentration. Guys, it's a concentration issue. Look, see, red balls in mason jars, right? Stupid. No, big idea. Watch. Guys, what's the concentration of red stuff right here? Really high. Because there's a high concentration of red stuff, there's a bunch of red stuff to turn into blue stuff. But now, 20 minutes later, what happened to the concentration of red stuff? There's less red stuff. The concentration has gone down. And if the concentration of red stuff has gone down, what will happen to the rate at which red stuff turns into blue stuff? It goes down. Guys, fundamentally, here's the deal. All chemical reactions are always slowing down, because they're consuming themselves. By definition, guys, reactant turns into product, and as reactant turns into product, there's less reactant. And because there's less reactant, the concentration goes down, and what happens to the reaction rate? It slows down. So guys, somewhere in your notes right now, you need to draw that line in the sand. And I would just simply write this: all reactions are slowing down. Understand, this is assuming that you're not replenishing the reactant that's going away. But guys, all chemical reactions slow down. So you all wrote down that statement, right? All chemical reactions slow down. Now you're ready to make this harder? Now write down the word because and finish the sentence. Ooh, things just got real. So guys, all chemical reactions slow down because. And I want you to finish the sentence and then we'll talk about it. What's the because? You ever thought about how weird a word because is? Good. You've never thought about that. Oh, yeah. Right. So guys, what's the because? Why are all chemical reactions slowing down? Because the concentration of what? The reactants is going down. Guys, by definition, reactions consume reactants. And as reactions consume reactants, they're destroying the very thing they need to maintain their speeds. So they're really self-destructive. Yeah.
What about when that improves?
That's interesting, because what you're going to find is that, and so I'm going to show you this graphically in a second, and it would be a really neat time to superimpose an equilibrium reaction over the top of it. But fundamentally what happens is in an equilibrium process, the rate of the forward reaction goes down, the rate of the backward reaction goes up, and eventually they end up at the same rate. And I think you can kind of see why. So the idea, right here. So guys, the question Isabel said is, what about equilibrium processes? So imagine that this were an equilibrium process. So what's happening to the amount of A? It's going down, so that's slowing down. But what is A turning into? Well, A is turning into B. So what's happening to the amount of B? It's going up. And if B can turn back into A, the speed of that backward reaction is increasing, and they reach equilibrium where their rates become the same. Then it stops, exactly, and then the concentrations become constant because the forward and the reverse reactions are undoing each other. Yeah, and that's what we're going to talk about as we transition into chapter 15 or whatever the next one.
It's all reactions that aren't that.
Well, no, because even here it still works because initially the rate of the forward reaction is decreasing. Understand it doesn't decrease to zero. So it's not a matter of whether or not it's decreasing, it's where it stops decreasing. Do you see what I'm saying? Go ahead.
There's this equilibrium reaction that they showed us. It was this container and it was going from...
Is they this summer?
Yeah.
Okay.
Clear to green to clear.
Yeah, right.
It slowed down.
Mm-hmm. Yeah. Yeah, because what's happening, those are what are called oscillating reactions. Interestingly, I actually did my senior project on these things when I was in college. But what happens is this. I'll just tell you quickly because nobody else has any idea what we're talking about. But what you're talking about is a reaction that is at equilibrium. It goes forward, it goes backwards, it goes forward, it goes backwards. But the whole reaction is slowing down because it's losing energy. It's actually exothermic. And so the way that I described it in my senior project is it's kind of like you're flying in a plane and you're throwing a ball backward and forward on that plane. So forward reaction, backward reaction, forward reaction, backward reaction. But the whole plane is losing energy as if it's landing. So within that plane, which is always dropping to lower energy, you can still have forward and backward processes even though it's losing energy overall. And that's why it slows down. Yeah.
So,
And that's what we're going to talk about when we talk about mechanisms. But let's just keep this simple for now. So guys, excuse me. Are you sold on the data? Okay, then let me show this to you graphically. Notice we've got a red line and notice we've got a blue line. And notice, guys, the x-axis is time. Notice the y-axis is numbers of moles. Here at time 0, how much red do we have? 1 mole, all of it. How much blue stuff do we have? None, right? We've got no blue. And then as the reaction goes on, what is happening to the amount of red? It's going down. What's happening to the amount of blue? It's going up. But guys, what does it mean? And I'm going to switch colors. What does it mean that these lines are parabolic? They are not linear because the reaction is getting slower. And so you guys, even though you don't need to know the calculus, you do understand that the slope of this line, rise over run. So guys, right here, this reaction, and you guys, do you all understand slope, rise over run? Here, the slope of this line is very, very steep. That was a little overdone. So guys, the slope of this line is very, very steep, showing that the rate of the reaction is very fast. So check this out. Why does slope represent rate? Well, guys, slope M is rise, change in y, over run, change in x. But guys, what are our units for y? Moles. What are our units for x? Minutes. What did we already agree those are the units for? Rate. Right? So guys, whether you know the calculus of this or not, what we're talking about are slopes of lines. Those are the first derivatives. Don't worry about it. But guys, what we're talking about here is this. Here we can see that that line is very steep, meaning the reaction is going fast. Now guys, what about this line? Steep? Also steep. But guys, what is the slope of this line? Negative. What is the slope of this line? Positive. What does it tell us that the slope of this line is negative? It's being consumed. That's a reactant. What does it mean that this slope is positive? It's being created. That's a product. But then guys, go out here. Look at what happens to the slope. Let's just look at this one. What is the slope here compared to there, more or less? Lower slope, meaning the reaction is slowing down. But guys, notice that the speed at which this is being consumed is equal to the speed at which this is being created. Let me say that again. And guys, if you're starting to tune out, focus, because this is going to kill you on the AP test. Notice that the speed at which this is being created is equal to the speed at which this is being consumed. Do you get that? You get that? That's not always true. Please hear this, guys. The speed at which the reactants are being consumed is not always equal to the speed at which the products are being created. In order to represent that relationship, you write what are called rate expressions. And I'm going to show you how to do that in a couple minutes. But guys, understand, right now, all we're saying is this. Products are being created, reactants are being consumed, and the rate at which that is happening is slowing down because the reaction is consuming itself. These, however, are not always equal. The rate of consumption and the rate of creation are not always the same, but we can always represent them writing what are called rate expressions. You guys good on those ideas? Okay, we're going to move forward. So, now guys, let's talk about how we're really going to do this, and you may want to write this down. So, we just talked about this idea of measuring rates, and we talked about the idea that we're going to measure rates in moles per minute, right? We're actually not. Guys, this is how we represent rate. Write this down with me. I told you that we use the example of moles per minute simply because it allowed us to talk about the mason jars. Guys, what we're going to do now is actually look at the units that we're actually, well, we'll look at it in a minute, but those are actually not the units that we're going to use. But this is the way we're going to represent this mathematically. So we're going to talk about average rates. Notice what we're going to do. Average rate, the rate of a reaction, is going to be given by the change in the number of moles of B divided by a change in time. Now guys, which is B, the reactant or the product? We'll talk more about this in a minute. But guys, when we measure reaction rates, we will not measure the rate at which the reactants are consumed. We will measure the rates at which the products are formed. We tend to chase the products. But we can simplify this by just doing this, right? Because what do the little triangles mean? Change. Now guys, let's make sure you're clear on this. Whenever we measure change, final minus initial or initial minus final? Final minus initial, so we'll say this. It's just final minus, I don't think you need to write this down because the change in moles of B is moles of B final minus initial, time is final minus initial. You okay? Y'all caught up? You're good? Okay. So guys, here's what we're going to do. In your notes, in just a moment, because what I'm going to have you do is we are going to calculate the rates of these reactions, the rate of that reaction, over 10-minute intervals. So guys, this then is our data. Oh, this works out great. We've got 6 groups. So here's what we're going to do. So Mella, and guys, we're going to be in rows. So this way, from you down to Jordan, you guys are going to be data set number 1. So on your own, you guys, each of you, calculate the rate of the reaction between times 0 to 10 seconds. And then let's have your guys' group right here, Jacqueline and down. You guys go 10 to 20. And then Matt, if you guys would go 20 to 30. And then around this way, Nathan, you guys go 30 to 40. And then Josh, let's have you guys go 40 to 50. And then Isabel, you guys go 50 to 60. So guys, whichever row you're in, write down the equation. Rate is equal to change in moles divided by change in time, and then do the math. Plug in the final and initial moles, plug in the final and initial time, do the math, and let's figure out the rate of this reaction about these time periods. So guys, again, we're going 0 to 10, 10 to 20, 20 to 30, 30 to 40, 40 to 50, and 50 to 60. Interestingly, it doesn't matter. But yeah, guys, do this with the blue. Do it with the blue. So we're just going to go rate is equal to change in moles, change in time, So guys, once you've come up with a number, then go down your row and confirm it with those around you. Okay, you guys ready? Okay, so here we go. Matt, what did you guys get here?
0.026 moles.
Hold on. 0.026. And guys, I'm just going to put units on everything. I love that Matt did that, but we're going to be moles per minute. So Jacqueline, what did you guys come up with for the second set? 0.02, and we'll go 2 decimal places like that. And then Jacob, what did you guys get? 0.014, and then 0.010, 008, and 0.006. Okay, so guys, let's analyze this data then. First of all, as time goes on, what's happening to the rate? It's going down. The rate is initially 0.026 moles per minute. By the end of it is 0.006 moles per minute. But also, and we don't want to dig into this too much, but it is worth mentioning, what is happening to the rate at which the rate is slowing down? It's also decreasing. So the difference here in rate is 0.006. The difference in here in rate is 0.002. If you're doing calculus, that would be a second derivative, which is like unto acceleration. Don't worry about it. But guys, what we now have is very real evidence that this reaction is slowing down, and the rate at which it's slowing down is slowing down, which isn't critical, but we do at least see that the reaction is slowing down. Now, guys, notice this. Interestingly, if we are going final minus initial, we all looked at B, right? So is the sign right? Are these positives? Is the amount of B going up, meaning a positive rate, or going down, a negative rate? They're going up because you all should have looked at B, which is the product which is being created. Now guys, what if I said, okay guys, let's do this entire thing over, only now let's look at the rate of consumption of A. All you got to do is put negative signs in front of these. Guys, this is an important idea, that the rate of creation and the rate of consumption are proportional, and the only difference would be the sign. You get the idea? Okay, go ahead. And that's not always true, which then gets us to writing rate expressions, which is where we're just about to get. Okay, so now guys, let's do this. We just answered that. Now we're ready, and I really don't think, please don't write this down, but here's the idea. So guys, we now understand some of these ideas about rates of reaction and the units moles per minute. But guys, up until now, those have been our units, moles per minute. But let's do this. Guys, why do reactions slow down as they go on? What's changing? The concentration, right? And here's the thing. Moles are not a unit of concentration. They are a unit of amount. And that's different than concentration. So here's what we're going to do. In order to unify our study, rather than measure rates in moles per minute, which doesn't directly influence rate because it's really the concentration, we're going to switch. So guys, if moles are a unit of amount, what are our units of concentration? Molarity. And guys, those are actually going to be our rate units. A minute is too long, so we're going to go seconds. And because rate is actually tied to concentration, we're going to measure these in concentration units, which are molarity. So guys, these, and this is it. You could circle, underline, highlight, whatever you need to do. This is it. These are our units of concentration, molarity per second. Moles per liter per second. But don't ever write that down.
So it's like we're doing liquids.
Not always. It's actually interesting because that's a great point, because now we're thinking not just liquids but solutions, right? But it also works for gases, because with a gas, because you understand molarity is moles per liter, right? That could be moles of solute per liter of solution, or it could be moles of gas per liter of volume. And it works there too. And you can almost picture why. Because the bigger the volume of the gas, the less frequently they collide. So you can really think of gases as having concentrations in moles per liter. And the logic works there as well. Yeah. Yeah, kind of. You could, but so Gwen's question was, what about alloys and metals? The problem is that metals, because they don't have a lot of freedom of position, the reaction rates would be a lot slower than you would suspect, simply because they can't move. So, but okay, so guys, here's what we're going to do then. We're going to take this idea and we're going to look at another reaction and look at concentration changes. So guys, we are going to look. Don't write any of this down, just trust me. Guys, we are going to look at the reaction of 0.1 molar butyl chloride as it reacts with water. So you're thinking to yourself, what on stinking earth is butyl chloride? Well, guys, what do you know about butyl chloride, even though you know nothing about butyl chloride? It's going to have some chlorine in it. Look for that. So guys, this is the balanced equation. So butyl chloride is C4H9Cl, and then we've got water. How do you know butyl chloride is the C4H9Cl? Because it's not water, right? And then guys, notice the products. You've got C4H9OH and HCl. So let's talk. What's HCl? Hydrochloric acid. This one you should actually maybe know. Guys, if we've got a substance with an OH, what kind of substance is that? It's an alcohol. So all you've got to do is take the but from butyl and add the alcohol idea to this, and this is what is called butyl alcohol or butanol. We'll talk more about that when we look at organic really quickly. But anyway, guys, here's the data from the reaction. It looks like this. So guys, what we've got here, and this is the way you're going to see, and actually I should tell you this. So guys, what we're going to do is we are going to track the concentration of butyl alcohol. This is a little bit, you know what, let me keep the reaction in sight for right now. This is a little bit of a departure from what we said, because we said normally when we track reaction rates, we track the product. But for some reason in this data set, they've got us tracking a reactant, and that's no problem. But guys, notice what they've done. They've given us time gaps. They've given us molarities, not moles. They've given us molarities, and then they've calculated for us the average rates. And guys, notice what's going on. The rate is going down. But the rate at which the rate is going down is going down. Here it changes by 0.2 times 10 to the negative fourth, then 0.1, then kind of back to 0.2 because of rounding errors. But if they gave us all of this, you would see that it's actually closing down on itself because the reaction is going slower. The only thing I don't like about this is technically these rates should all be negative because the reactant's being consumed, but you can see that the reaction is slowing down. You okay? Okay. All right. So guys, I actually have this then for you graphically if you're interested in seeing it. But if you take this data and graph it, the idea is here we've still got time and we've got molarity. You can see that the molarity of the reactant is decreasing. You can see that the slope of the line is ever decreasing as well, meaning up here the reactant's going away quickly. Down here the reactant is going away more slowly. And you may have heard of these ideas of instantaneous rates, which again are back to calculus and first derivatives. You don't need to worry about it. You just need to know that the rate is decreasing. You guys okay? All right. So, guys, we got one more thing to talk about. We got about 6 minutes. We're going to get this done, and it goes like this. Guys, the last thing that we need to talk about are rate expressions. Do write this down. Here's what's going to happen. Guys, this is probably the easiest thing you're going to learn in this unit. And most of you are going to miss this on the test. And when you miss this on the test, here's what I want you to do. Come up to me when I give you your test back and go, Mr. Namberger, I know that you warned me and I just got it wrong because I forgot. Because guys, here's the problem. You today are going to learn to write rate expressions. And you're going to be like, oh, this makes sense. Oh my goodness. Okay, I know how to write rate expressions. And then guys, we're not going to talk about rate expressions for the rest of the unit. This is going to disappear into a distant memory. And then when you sit down to the test that we're going to take, the first thing that it's going to say in the first free response question is write the rate expression. And this doesn't even make sense to you, but this is what you're going to do. You're going to write the rate expression, and you're going to write the rate law. The reason that you're going to write the rate law is that's what we're going to talk about for the rest of the unit. And you're going to get so used to writing rate laws that you're going to forget about rate expressions. And when the test says write the rate expression, you're going to write the rate law and you're going to get it completely wrong. So guys, I don't know what you need to write in your notes, but you need to write something that says, don't forget me. Because these are a minor detail, but they will ask you to do these on the AP test. Okay, so these are what are called rate expressions. So, what is a rate expression? Well, guys, a rate expression represents a stoichiometric relationship. Where do we get stoichiometric relationships? Balanced equations. So, guys, here's the trick. In the last two examples that we've looked at, red balls turning into blue balls, or the butyl chloride and the water turning into the butanol and the hydrochloric acid, these have all balanced with ones. The stoichiometric ratios in both of those processes was 1 to 1 or 1 to 1 to 1 to 1. But it was all ones. But what if it ain't a 1? Well, guys, then we've got to account for that. Exactly, precisely. It's all stoichiometric. So guys, the question then becomes this. What if they aren't 1 to 1? You ready? I made this up all by myself. Okay. So you remember our red thing, our mason jars, red thing, blue thing? Well guys, what if it goes like this? Don't try to write this down. This is so cool, there's no way you can write this down. Actually, it's not, but you can't write it down. It's not that cool. But it goes like this. Guys, imagine if it goes like this. Instead of a blue A turning into a red B, what if every A turns into 2 Bs? Well, then the relationship might look like this. So we are going to start with a molarity of some A and some B. And guys, if we lose one A, see how this is like our starting point. If we lose 1A, how many B's will we get? 2. And what if we lose another A? We get 2 more B's. And what if we lose another A? We get 2 more B's. So guys, you can see that these rates are different because A is dropping and B is rising, but it's not happening at the same rate because every A that we lose, we gain 2 B's. You can visually see that these are not happening at the same rates. Now, guys, here's the problem. Did I put this in my notes? Oh, I did. Here's the problem. Guys, these have got to be equal, right? We got to make these things equal. So here's the question. What can we do to make this stack equal to this stack? What do we need to do to make these stacks the same? Well, not get rid of B. What do we need to do? So, guys, the first thing we should do is, which way is this pointing? Up. Which way is this pointing? Down. Why does this one go down? It's a reactant. It's being consumed. Why is this one going up? It's a product. It's being created. So, guys, what can we do mathematically to flip this over? Make it negative. Right? Doesn't a negative sign just flip it over? So the first thing we're going to do is we're going to make the rates for all the reactants negative, which functionally flips it over. Did I flip it over? I didn't flip it over. But guys, what that'll do then is it'll bring, oh, it did. That should have disappeared. Pretend it's not there. Do you see what happened though? Making this negative makes this flip over and now it's going up. So now we've got them pointed in the same direction, but they still aren't equal. So what have we got to do to make this look like that? We're missing some, right? So what we're going to do, guys, is we're going to cut that guy in half. And when we cut that guy in half, now they're the same. Get it? So guys, look at what we did. The first thing we did is we took the rate at which the reactant is being consumed and we made it negative, functionally flipping it over. Then the next thing that we did is we divided by 2. Why did we divide by 2? Because of that 2. So when you're writing rate expressions, here's what you do. Make the rates for the reactants negative, that flips them over, and then divide by the coefficients, and that accounts for the fact that it's not happening at the same rates. You get the idea? So here, let's do it together. So guys, it goes like this. Rate then, and you want to scratch this down with me. Guys, rate then is equal to, do you want to come back and do this after? So what if we finish and then take break after? Okay, so guys, the way that this goes is we go rate is equal to, this is the rate expression for this. Rate is equal to the change in, do you remember what the brackets mean? Molarity. The change in the molarity of A divided by time, and that is equal to the change in molarity of B divided by time. Remember, rates are just change in molarity, change in time. But here's the problem, guys. This isn't actually true. These are not actually equal. They're not even proportional yet. Guys, they are actually not equal. So what do we need to do to make them equal? Well, the first thing we've got to do is multiply that by a negative. That flips it over. But we're still not done. What else do we have to do to make them negative, or to make them equal? Divide that by 2, so put a 2 in the denominator. And now they're actually equal. So what we just did is wrote the rate expression for this process. Go ahead.
Why didn't you just multiply it?
You could have. You could multiply A by 2. Well, but understand that this is the accepted way to do it. So technically, you could have put a 2 in the numerator there and you'd get the same answers. And if you did that on the AP test, they wouldn't mark it wrong, but it wouldn't be their first answer, because the accepted way to do this is to divide by 2 rather than multiply that by 2. It would get even more complicated, though, if this were a 3. Right? Because then you'd have to multiply this by 3 and that by 2. Or just divide by 3 and divide by 2 and not worry about it. You know what I'm saying? It's easier to just divide by the coefficients and then you won't get them crossed up. Yeah.
So is this how they want us to write it, or do they want numbers actually?
No, so what, okay, so good question. So what we've just done is we have written the rate expression for this process. Then what they'll do in the next step is they will give you a rate. And they'll say, for example, if A is disappearing at a rate of 0.5 molarity per second, at what rate is B being created? Do you want to try it?
Yeah.
Okay, so guys, let's do this. I think I have an example here. So imagine this. So this is the decomposition of iodic acid. So iodic acid decomposes into hydrogen and iodine. Write the rate expression. Guys, go ahead and do it in your notes. Write the rate expression.
For hydrogen.
The whole thing. On the test, it'll say, here's the reaction, write the rate expression. And by the way, guys, while you're working on this, we're going to be fine in third period relative to what we're doing. We don't have a ton of work to get done third period, so we'll be good. You okay? Are you done? So guys, it goes like this. Rate is equal to the change in concentration of HI divided by change in time is equal to the change in concentration of I2 divided by change in time is equal to the change. I guess I should keep these in order. H2. And then the change in concentration of I2 divided by the change in time. So those are our fundamentals, but these are not equal. So what do we need to do to make these equal? Well, what do we do to the reactants? Make them negative. So that would be negative. And then everything else that we've got are products, so those don't become negative. And then we divide by coefficients, so we divide that by 2. Is that okay? Okay, now, okay, I don't have data, so let's make something up. So let's say that the H2, that the rate of consumption of H2 is 1 molarity per second. Consumption. Oh, I said H2, I meant HI. I'm sorry. So the consumption of HI is 1 molarity per second. What is the production of H2? And you can probably look at this and see that it's 0.5. Because this is being reduced at half the rate this is being consumed. But guys, let's do this mathematically. Figure out how this works. You understand what we're saying? We're just easy numbers. But the idea is this: the rate of consumption of HI is 1 molarity per second. What is the rate of production of H2? See the question we're answering. This is what the solution would look like. Because what we're going to do, and I'm going to switch colors, is we are simply going to focus in on this portion of the expression, because this gives us our HI and our H2. So notice what we're given. We're given 1 molarity per second. So guys, where does 1 molarity per second go? That's the part that I just put in the box. So we've got molarity, change in molarity, and change in time. So functionally what we've got is negative divided by 2, and then in there goes the speed, 1 molarity per second. Is that okay? And then what we're solving for is the rate at which this reactant or this product gets formed. And so what we want to know is functionally all of this. We want to know the change in molarity over the change in time. So this entire thing then becomes our x. And now we just solve. And 1 divided by 2 is a half. So the rate of that reaction would be a half, or 0.5 molarity per second. So now you're going, wait a second, what about the signs? What about the negatives, right? Well, guys, this rate, the rate for HI is actually the rate at which it's being consumed. So technically that's negative, which means technically this is a negative, and a negative times a negative is a positive. Now understand, they won't nail you for that on the AP test, neither would I. So if you didn't identify that as being initially a negative rate, so long as you knew that the rate of production is positive, you're okay. But the rate of this then would be 0.5 molarity per second. You guys okay? Okay, so guys, you'll see some of those in homework to fiddle with that aren't quite that simple. Here then is your homework.